Okay, so last time, remember, we started discussing general methods for solving certain boundary value problems. And so for these problems, we're considering the same partial differential equations that we've been looking at for the past few weeks, in particular, the wave equation and the diffusion equation. But we're no longer looking at the case where the domain is the whole real line. We're restricting to some finite interval between, say 0 and some number L. Right. Right. And so the domain is restricted to, say, 0 less than or equal to x less than or equal to L. And we're going to be given information about how the solution behaves at the two boundary points, right? Right, so about u of 0t and u of lt, right? So these are like the boundary values. Right, and so we've already seen an example where we're assuming that both of these quantities, u of 0t and u of lt, are both equal to 0. And that's going to be a pretty common assumption for these types of problems. We'll also see another condition involving the derivatives of u being 0 at these boundary points. We'll discuss that a little bit later today. And so we saw last time, of course, you were first introduced to these types of problems in one of your homework sets, where you work through how to derive like a candidate for a general solution formula for the wave equation on between 0, when x is between 0 and pi, with boundary conditions where the solution is equal to 0 at these endpoints. And so once you arrive at this formula, you're led to some pretty significant and challenging mathematical obstacles. And so remember that, let me restate the problem. Well, we were led to the following problem. So let's suppose that phi of x is a given function, which will correspond to some initial data. Right, so for example, this phi of x could be the initial position of your wave with these boundary conditions. And so the question was, when is it possible to write my function phi of x as a possibly infinite sum of combinations of sine waves at different frequencies, at some discrete collection of frequencies? For example, when is it possible to write phi of x is sum from n equals 1 to infinity of some number an times sine of n pi over L x? Right. So as we saw, in order to solve or to write down solutions for the boundary value problem associated to both the wave equation and the diffusion equation, you need to be able to answer this question, right? So this is kind of the key question that will motivate essentially all of the lectures for the next several weeks, right? And so today we're going to begin slowly addressing this question. Right, and so in order to go into more detail, I want to first review some material from linear algebra, which will help give you some analogies to work with as we study this problem. If you haven't taken linear algebra before, it may be worth like reviewing some of the concepts that I'm about to summarize, like look at the Wikipedia article, or try to open up some notes related to linear algebra. In this class, you're not going to have to do many calculations involving linear algebra. but a lot of the ideas we're going to use over the next several weeks are motivated from ideas that are used in a somewhat simpler setting in a linear algebra class. So it may help to go back and review this stuff if you haven't seen it in a while or if you haven't seen it before. And so we're going to begin, right? We're going to begin with some linear algebra recap, in particular related to eigenvalues. Because it's going to turn out that this type of problem has a very kind of deep and important interpretation in terms of things that are related to eigenvalues and eigenvectors and things like this. Okay, and so let's just remember from linear algebra, what are eigenvalues? Well, we have to begin by, as is common in linear algebra, is by fixing a particular matrix. So I'm going to suppose A is an, say, M by M square matrix, where M is bigger than or equal to 1, but otherwise arbitrary. In particular, we're not going to just restrict ourselves to 3 by 3 or 2 by 2 or something like that, right? Okay, well, remember, if you have an M by M matrix, it acts on vectors with M components, right? So given a vector X, which I'll write with an arrow, which has M components, say x1, x2, etc., all the way up to xm, we would say this is in bold R to the M. The matrix A acts on X. In the following way, right? So I can apply the matrix A to X, and well, let's suppose the columns of the matrix A are indexed by like A1, A2, etc. Well, then the action of A on the vector X is given by this formula. It's xm times am, where these vectors A, AI are the columns of the matrix A. Right, sometimes the shorthand is, maybe I could write it like this. Right, so these things are, the AIs or A sub i's are vectors that are the columns of A. Right, and so if you go back to your formula for how a matrix operates on a vector or transforms the vector, you can write it in this manner. Right. Okay, and so what are eigenvalues? So let's recall the definition. Well, an eigenvector, say V in Rm, meaning it has M components in the vector, with an associated eigenvalue, right? Every eigenvector will have an associated eigenvalue, lambda, is a vector such that when I apply A to this vector, the resulting object is just a scalar multiple of the vector, and in particular, it's equal to lambda times V. Right, and so when I say it's an eigenvector, it's an eigenvector for the matrix A, right? All this depends on the matrix A. Right. And so, right, so what is this saying? Well, let's go back to this formula for how the matrix acts on the vector. Notice that A transforms the input vector X into a new vector, which we denote by A of X. So this is kind of like the differential operators we've been seeing throughout the semester, where the differential operator will take a function and it will transform that function into a new function, which involves derivatives and things like this. This is very similar to thinking about a matrix which is acting on a vector, because the matrix will take a vector as an input and give you a different vector as an output by following this rule. And so eigenvectors are special vectors for the particular matrix you're given, such that when you apply the matrix to that vector, it only scales it, right? It doesn't do anything more complicated than just scaling it. So this turns out to be these types of vectors turn out to be very useful, because in many cases you can basically find a nice basis for your space and consisting of eigenvectors for this matrix, which make all sorts of computations a lot easier to do in linear algebra. So this is one context in which they arise, and you've probably seen this before if you've taken a class in linear algebra. Right. And so, okay, that's a very rough, quick recap of what eigenvectors are with associated eigenvalue lambda. And so what I want to do is talk about how this arises, how these types of things arise in the study of partial differential equations. Great, so we're going to talk about eigenvectors. I'm going to put quotes around it because they're technically called something else. Eigenvectors in PDE. And I'm not going to give you the most abstract definition. We're just going to look at a particular example. And in particular, we're going to look at, well, let me define a function Vn of x. Now, this is no longer a vector v, it's a function. And I'm going to choose this function sine of n pi over Lx. Right. And it's going to have the domain given by x is between 0 and L. Well, notice that we have a specific boundary condition, which is related to the boundary condition we were studying for the PDE. So if I look at Vn of 0, this is 0. And also, well, if that's just because sine of 0 is 0. Also, if I look at Vn of L, this is equal to sine of, well, x gets replaced by L, and then that cancels with the other L. So I have sine of n pi. N is an integer, right? And so the sine of any integer multiple of pi is 0. So Vn of L is equal to 0. Right. So these functions have the given boundary condition. Right. So let me call it quote unquote 0 boundary condition. Which just means they're equal to 0 at the boundary points. Right? Okay, and so what does this have to do with eigenvectors? Well, it turns out that if I pick a particular differential operator, these functions act just like eigenvectors for this operator, except instead of a matrix, it's a differential operator, right? And so we're going to consider the differential operator, which I'm going to call A, to match up with the matrix notation from before. And it's going to be -1 times the second partial derivative with respect to x. And it's going to be acting on functions defined between 0 and L. Okay, so let's say functions g of x defined on, say, x is between 0 and L, with 0 boundary conditions. Oh, sorry. Okay. And so this is a very important point that the book suppresses in the exposition related to this, which is when I'm looking at this differential operator, I want to really specify what is the domain of the functions that it's acting on. Because this turns out, it's not going to be clear now why this can lead to complications, but we'll see examples in subsequent lectures where we change the boundary conditions and the things I'm about to talk about will change, right? And so this is like the domain of the operator with specified boundary conditions. Right, and so all this says is that when we're applying this operator to functions, we're only going to consider functions that are defined for x between 0 and L with the specified boundary conditions. And this is okay because we're interested in solving a particular partial differential equation where all functions that are interesting for this equation will satisfy these two properties, right? So we get the boundary, the domain just from the PDE that we're interested in, right? Okay, and now what happens if I apply this matrix A to these vectors Vn, or sorry, these functions Vn, right? So what I'm going to do is apply, calculate A applied to Vn, which technically is a function of x, right? A of Vn of x. Well, this is equal to negative second order derivative of sine of n pi over L x, right? And so, okay, let's calculate one derivative. Well, if I calculate one derivative, I have negative d dx of n pi over L times cosine of n pi over Lx, just using the chain rule, right? Of course, I can factor out the n pi over L, and then I just have d dx of cosine of n pi over Lx. And so now if I calculate one more derivative, I'm going to get, well, derivative of cosine is negative sine. The negative will cancel out with this other negative, and then I have to use the chain rule again. So I'm going to end up finally with, well, I'm going to have n pi over L multiplied by itself. So n pi over L squared. And then I'm just left with sine of n pi over L x. But notice this is exactly n pi over L squared times Vn of x, right? And so in particular, this function is the same, right? Vn has appeared again. And so what did this operator ultimately do? It just multiplied the function by a number, right? So this is, I'm going to call this lambda n. And what we just showed is that a of Vn of x is equal to lambda n times Vn of x, which should remind you exactly of what we talked about before with eigenvectors for a matrix. And so, right, we have exactly this formula here, just in like the function setting, right, where the vectors are replaced by functions, and the matrix A is replaced by a differential operator. And so what do we have? Well, again, yeah. So something that looks exactly like the eigenvalue equation, right? And for this reason, well, we say that lambda n, which is equal to n pi over L squared, is an eigenvalue for the operator minus d dx squared, d squared, sorry, yeah, which was A, on the domain that was specified before, right? So on the domain with 0 boundary conditions specified before, right? So the domain is what I have boxed off in blue here, right? Right, so we say lambda n, this value n pi over L squared is an eigenvalue for the operator minus d second derivative with respect to x on the specified domain with eigenvector, in quotes, Vn of x, which is equal to sine of n pi over L times x. Right, so these functions, sine of n pi over Lx, act like eigenvectors for this operator with eigenvalues given by lambda n, this formula over here. Since they're not actually vectors, what we traditionally do is just replace vector by function. So these will typically be called eigenfunctions for the operator with eigenvalues given. That's above. And so I want to specify again that it's important to indicate what the domain is. Like, this seems like a kind of an obnoxious or pedantic technical point, but we will see soon that if you change the boundary conditions in the domain, or if you change, so if you change the boundary conditions on the domain, it's going to change what types of eigenfunctions you can find or what the eigenvalues could be. And well, if you change the length of the domain, you can already see that if we replace L by like L squared or something, the eigenfunctions are already going to change, right? So this has an impact on what the eigenfunctions are. So always make sure that you understand what the domain is. Right. And so here's the analogy. Right, so here's the basic analogy. So the differential operators are like matrices in linear algebra. And then functions are like vectors. And right, eigenfunctions are like eigenvectors. Right? So a lot of these ideas are things that you would have encountered in linear algebra, but now they're in the setting of functions rather than vectors. And in fact, you can think of a vector as a particular simple version of a function where its domain is just the 1 through m, and say at value 1, it outputs whatever the component is for that entry. Right, so this actually is like a legitimate generalization, direct generalization of things that are done in linear algebra. The main point, though, is that in linear algebra, you study finite dimensions, finite dimensional. And in partial differential equations, things are necessarily infinite dimensional. And so a lot of what we're going to be doing for the next few weeks is sort of like infinite dimensional linear algebra. This is a good way to think about it. Okay, and continuing along these lines, I want to review a little bit more from related to eigenvalues from linear algebra. So let me call this linear algebra recap 2. And I just want to briefly review some facts related to something called an eigenvector decomposition, which I alluded to above. Right. And so this is something which turns out to be very useful for applications of linear algebra and is one of the main reasons why eigenvectors are so important. And so the eigenvector decomposition works in the following way. So suppose your matrix A from above, which we're assuming is an M by M matrix, is diagonalizable. Meaning that A is similar to a diagonal matrix. Similar is in quotes. I'll come back to that in a second. A diagonal matrix is just a matrix that has all the non-zero entries are in the diagonal of the matrix, right? So outside the diagonal of the matrix, everything is 0. Similar means I can change the basis for my space to transform the matrix A into a diagonal matrix. Right? If you didn't take linear algebra before at this level, that's okay. What I'm saying now is probably nonsense, or sounds like nonsense if you haven't seen this before. You're not going to have to do any calculations involving these ideas, so it's okay to just ignore this section. If you've never been exposed to this side of linear algebra, it's okay to ignore what I'm about to say and then just focus on what I say about PDEs below it. Right. But if you have encountered this before, it will hopefully give you some analogies to think about, which will motivate what we're going to do later on. Right, okay, so let's suppose that we're given a matrix which we know is diagonalizable. Then you can always find a basis for Rm, say V1, V2 up to Vm, consisting entirely of eigenvectors for A. Right, and moreover, you actually know more. It turns out that this basis can be chosen to be an orthonormal basis, meaning perpendicular and normalized, right? So moreover, this basis is orthonormal, meaning the following. So if I take the dot product of any two vectors, say vi and vj, that this is equal to 1 if I is equal to j and 0 otherwise. Right. And so in particular, this says that they're perpendicular if I is not equal to j. Right. And so in particular, what does it mean that these form a basis? Right. So for any other vector, it means I can write that vector as a linear combination. Right. Any other vector x, which is in Rm, I can write x as a sum, say C1 times V1 plus C2 times V2, et cetera, all the way up to Cm times Vm, right? This is just because they form a basis. Right, and so any vector in the space I can decompose as a linear combination of eigenvectors for the matrix, right? And so this is what I mean by eigenvector decomposition. And so actually, more is true. We can say a little bit more. For example, you may want to know for computational purposes, like what are these coefficients? Like what is C1 equal to, what is C2 equal to, and so on. Well, we can actually calculate these using the fact that the vectors are perpendicular. Right. We can calculate C1, C2, et cetera, in terms of the vectors. In terms of the eigenvectors. In particular, well, notice that, let's say I take the dot product of my vector x with v1, right? If I take the dot product of my vector x with v1, that's going to be sum from I equals 1 to m of ci, using linearity of the dot product, ci times x dot vi, or sorry, ci of vi dot v1, right? Because I'm taking the dot product with each of the terms above, and so I'm taking dot product c1 v1 dot product v1 plus c2 v2 dot product with v1 plus c3 v3 dot product with v1 and so on until I hit the end. That's just the sum I've written here. But recall from above that this dot product is 0 unless I is equal to 1, right? Because of the orthogonality or perpendicular property up here. And so this whole thing just simplifies to C1 V1 dot product with itself. But dot product of V1 with itself is just 1. So this simplifies to C1, right? And so in particular, the coefficient C1 is just given by taking the dot product of your vector with V1, right? So similarly, if I take dot product of x with v2, I get c2. Dot product of x with v3 gives me c3, and so on, until dot product of x with vm will give me the coefficient cm, right? So you can recover all these coefficients by taking the dot product of your vector with the respective eigenvector for the matrix, right? And so therefore, I can decompose my vector x as sum from I equals 1 to m of x dot product vi, which is a number, right? Because dot products are scalars, times the vector vi, right? And so this is more precisely what I mean by like an eigenvector decomposition, right? Because the vi's are eigenvectors for A. Right. One reason this is useful is because I can now better understand the action of the matrix A on the vector x, because since A is linear, when I apply A to x, it's just going to be a sum of A applied to each of these terms. But the dot product is a constant, so I can factor that out because the matrix is linear. And then I'm just looking at a sum of a combination of A applied to the different VIs, but the action of A on each VI is very simple. It just scales it, right? And so this makes it a lot easier to work with the matrix. Okay, and so now what we're going to talk about is the analog of this eigenvector decomposition, but in the infinite dimensional setting when we're working with functions and differential operators in places of vectors and matrices. Right. And so let's consider now the PDE setting. And so let's recall that we're working with our matrix A is now going to be replaced by negative second partial derivative with respect to x. Right, and then the eigenvectors or eigenfunctions replaced by given by these sine functions, right? So Vn of x is equal to sine of n pi over L times x. And notice in particular that the eigenfunctions are indexed by integers, right? Right, so n ranges from 1 to 2 to 3 and so on up to infinity. And so it's kind of like what we have above, where we have some list of eigenvectors for the differential operator, except instead of having some finite number, we have an infinite list from n equals 1 to infinity. It's discrete, meaning like we're not looking at a continuum of frequencies or a continuum of eigenfunctions, but there's still one for every integer from 1 to infinity. Right? And so from before, we were interested in the following. We wanted phi of x, which was a given function, right? So this is just some given function on the domain of the differential operator. And we wanted to write phi of x as a sum from n equals 1 to infinity of some an times sine of n pi L over x. But these are just, I can simplify this and write this as Vn of x, right? So Vn, remember Vn is sine of n pi over L times x, right? And so this should remind you a lot of the expression we have above, right? So here I have a vector in Rm, and I'm writing this as a sum from I equals 1 to m of some ci times the vector. And this vector happened to be an eigenvector for my matrix. In the PDE case, we're looking at a problem where we're given a function which is on the domain of this differential operator, and we want to write our function as an infinite sum of eigenfunctions for the operator, right? Each of these is an eigenfunction, right? with some coefficient an, right? And so we don't know what these coefficients should be. We also don't even know if this is possible yet, but we're just trying to motivate things. And so this should remind you of an eigenvector decomposition, right? So this is not an eigenvector, but an eigenfunction decomposition. Right. And so it's exactly this decomposition which we'll be focusing our attention on for a while now. And so in order to actually understand this problem, one thing you can hope for is, is there some way to calculate an? Like, let's forget about convergence issues for now. Right? Is it possible to determine an? Ignoring convergence issues, like we're going to forget for now about the issue of whether or not the series converges. Since it's an infinite sum, this is an important issue, right? Because of course, not every infinite sum will converge. For now, we're just going to focus on the question of, is it possible to determine an? Right. And so another related question, or another question which turns out to be related is, does there exist any notion of perpendicularity or orthogonality, which we used previously? Right, because, well, if we go back to this eigenvector decomposition, since these eigenvectors were perpendicular or orthogonal, we had this very exact formula for calculating the coefficients Ci, right, using the dot product. So I guess the one way to phrase this question is there a notion of the functions being, I'll put it in quotes, perpendicular or orthogonal. Orthogonal is just a fancy word for perpendicular, but it's commonly used in linear algebra, so I just wanted to use that here. That would allow us to find a formula similar to what we saw above. Or like say an easy formula for the ANs. Right, and so what do I mean? I mean something like AN, I'm going to put this in quotes because it's not mathematically rigorous, but something like, well, how did we calculate CI? We just took the dot product of the vector x with the corresponding eigenvector. So is there some notion of like a dot product that would allow us to calculate AN by taking the dot product of phi with one of the VNs, right? This is what I'm talking about, right? Because if we could find such a formula, it would allow us to answer the first question, right? Right. Right. Okay. And so this is what we're going to turn to now, answering these two questions. I mean, at this point in a live lecture, I would pause to ask for questions. If you're confused, what you should maybe do is pause the lecture and rewind it and go over things again, or maybe like spend some time reviewing some of these concepts from linear algebra if this was too fast. On the other hand, as I said before, we're using these facts from linear algebra as motivation. If you haven't been exposed to these things before in a linear algebra course, you just won't be able to, I mean, it'll just be less motivated, but you can still do the PDE study that we're gonna talk about. Okay. Right, and so again, the key point here is that it was the orthogonality, or the fact that the eigenvectors are perpendicular, that allowed us to get an easy formula like this, right? Because we use the fact that they're perpendicular to derive this formula, right? This was sort of, in this example, the key step was that all of the terms are 0 except 1, which allows you to determine what Ci has to be for any given I. And so the first thing we want to do in the PDE setting is to try to find some version of this orthogonality principle. And so this took a while to develop, but I'm just going to write down what it is, right? I don't want to make it seem like a mathematician just discovered this the second they encountered this problem, right? This is something that was developed after a lot of thought. And so we're going to talk now about orthogonality in the PDE setting. And then in particular, we're going to focus on the setting for the boundary value problem we're considering with the particular eigenfunctions we've been looking at. And so it turns out that, well, let me write this as a theorem, although it's really just a calculation, calculating some integral. If I look at, well, let me write Vn of x is, let's just remind ourselves what these eigenfunctions are. So the theorem says that if I look at the integral from 0 to L, which is the domain for these functions, right? So we're looking at the domain 0 less than or equal to x less than or equal to L. If I integrate Vn of x times Vm of x dx, that, well, if m is equal to n, this is equal to L over 2. However, if m does not equal to n, it's equal to 0, right? So again, if I integrate two of my eigenfunctions, if they're not the same eigenfunction, then the integral is 0, integral of the product. And if they are the same, then the integral is equal to L over 2. And so what does this mean? This means that if I multiply both sides by 2 over L, well, then this will be scaled to 1, and then dividing 0 by this number doesn't change the fact that it's 0. And so we get this result, which should be compared with the formula for the dot product for the orthogonal eigenvectors up here, right? Right, so exactly in this formula here, we have the same thing, right? If the indices are the same, the dot product is 1, otherwise the dot product is 0, which corresponds to the functions being perpendicular. Well, for our eigenfunctions associated to the PDE problem, it turns out that they have a similar property, which looks a lot like orthogonality from linear algebra, right? Where if I integrate, instead of taking the dot product, I'm now looking at the integral on the domain of the product of the two functions, which is, this really is kind of like a higher dimensional or generalized dot product, right? But you can also just think of it as an integral, and that's fine. Look at the integral of Vn times Vm, then this is, as long as I divide by 2 over L, this is 1 if the eigenfunctions are the same. And otherwise, if they're two different eigenfunctions, you get 0. Right, so this is kind of like the formula Vn dot Vm equals 1 or 0 if n equals m. Right, and so this is like a notion of a dot product. Okay. And so we'll see that we're going to be able to use this. So let me just write this out. This is what I mean by the orthogonality for these functions. And so we'll see we're going to be able to use this orthogonality property to find a formula for the an, which is going to be very similar to what we saw previously in the linear algebra case. But first, let me just sketch the proof of this theorem. It'll be a good vehicle to remind you about some trig identities and some facts from calculus. Right, and so what I'm going to do first is, let's suppose first that n does not equal m, right? And so we want to show that if I look at the integral of sine of m pi over L times x. Sorry, let me rewrite this. We want to show that if we look at the integral from 0 to L of sine of m times pi over L times x times sine of n times pi over L times x dx, we want to show this is equal to 0 for m not equal to n, right? And so we're going to use the following trig identity. So the trig identity is if I look at the sine of some number a times the sine of some other number b, that this is always equal to 1/2 cosine of a minus b minus 1/2 cosine of a plus b. And so a lot of people may not have seen this identity before, so let me briefly review where it comes from. Well, you're probably more familiar with, although you may not remember how to prove, the double angle formulas. If you look at cosine of, say, a plus b, this is the same thing as cosine of a times cosine of b minus sine of a times sine of b, which is exactly what we have above. And also, if you look at the cosine of a minus b, well, you're just going to replace b by minus b above. Since the cosine is an even function, this stays the same. And then, well, since sine is an odd function, the minus sign gets flipped, and you get this. Right? And so let's call this one equation I, and this one equation 1 or equation 2. Well, if I look at, let's say I look at equation 2 minus equation 1, this shows that, well, the cosine terms on the right-hand side all cancel. Then I have sine of a times b minus negative sine of a times b, so I get 2 sine of a sine of b. And this is equal to cosine of a minus b minus cosine of a plus b, right? And so then I just divide by 2, right? And so that's where this comes from, right? Now you can ask, okay, maybe I've seen the double angle formulas before, but I have no idea how to prove them. So I'm not going to prove the double angle formulas now. You've probably seen the proof at some point way back many years ago in like a trig class. What we will do, though, is very soon we'll see an easy way to prove all sorts of trig identities like this. And so we're going to, when we discuss things called complex exponentials, which will be useful in a few weeks, as a byproduct of this discussion, you're going to have a new method that makes it easy to understand why all of these trig identities are true. So one of the nice things about this subject, which you'll see soon if you haven't already, is that it gives you an easy way to understand where all these super complicated trig identities come from using complex numbers. Great. Okay, but what we will do now is just plug in this formula to the integral, right? So this tells me that integral from 0 to L of sine of m pi over L x, sine of n pi over L x is equal to integral from 0 to L of 1/2 cosine of the difference of the two arguments, and then minus 1/2 times the cosine of the sum of those two terms. Right? Okay, well now I just have two different integrals involving cosine, right? So I have 1/2 integral of cosine of right, so this is what I end up with. Right, But now it's easy to see that both of these integrals are going to be 0. Why? Because, well, I have both of them will, the antiderivative is always are of the form plus or minus some number c, some constant, times sine of pi times n minus n plus or minus m over L times x, and you're evaluating when x ranges between 0 and L. And so, well, when I plug in x equals L, I have sine of an integer multiple of pi, so I get 0. And of course, when I plug in x equals 0, I also get 0, right? So these are always equal to 0, right? And so, in fact, both of these, you don't even need to use the fact that maybe the positive and negative integrals cancel. No, and in fact, both of these are just equal to 0. If that was too fast, again, just pause the lecture and you can just calculate this integral pretty quickly, show it's equal to 0. Right, and so that proves the first part, right? So this shows that if m is not equal to n, then when I integrate the product of two distinct eigenfunctions, I get 0, right? And so finally, we need to prove the second part, which is if I integrate from 0 to L of the same eigenfunction times itself, then I get L over 2, right? Right, so next, suppose that m is equal to n. In this case, we want to show that if I look at integral from 0 to L of sine of m pi over L times x times itself, so just squared dx, that this is equal to L over 2, right? Because then I can just divide by 2 over L and it'll be equal to 1. And to prove this, we'll just use this is probably something that you've seen in an introduction to calculus class for calculating integrals of trig functions. We'll use the fact that if I look at the sine of a squared, you can write this as 1 minus 2 times the cosine of 2a, or sorry, of just a, divided by 2, right? And so we're going to plug this into the integral. Again, this is a trig identity, which you may not remember why this is true. We'll see an easy way to prove it later on in the semester. If I plug this in, well, the integral is now equal to 0, integral from 0 to L. Well, I have 1/2, and then I have minus cosine of, in this case, a is m pi over L times x dx. And so I can split this up into two terms. The first is the integral from 0 to L of 1/2 dx. And then the second is the integral from 0 to L of the cosine term. Right? So the integral from 0 to L of 1/2, this is just 1/2 times L, which is L over 2. And then using a similar argument to what you would have done for the first part, you can just show that this last term will just integrate to 0, right? And so that's the proof. Right. Okay, and so what this theorem really gives us is a notion of orthogonality or functions being perpendicular, where the functions are the eigenfunctions for the differential operator, right? And so reviewing what I said before this argument, well, we saw that if I can write my vector x as a linear combination of eigenvectors which are perpendicular, in fact, we really only need to use the fact that the vectors were perpendicular or orthogonal, then I can calculate the coefficient, right? And you can calculate the coefficient just by taking the dot product of x with the corresponding eigenvector. And so now, well, I want my function phi to be some combination of the eigenfunctions. I'll be able to calculate the coefficient we would expect now that we have a notion of orthogonality, which is given by this theorem. We'll be able to calculate the coefficient by using this property. And so this is the next thing we're gonna look at. Right, so this is the next theorem, which is right. Right, so this is the theorem for calculating an in a sine series. Right, so maybe I don't think I've used this terminology yet. So if I go back up here, in this case, all our eigenfunctions are sine. So this is usually called like a sine series. Sine Fourier series. Sometimes Fourier is the mathematician who originated a lot of this theory. We'll talk more about him and Fourier series shortly. For now, so just sine series is okay. Right, and so this theorem tells us how to use the previous theorem to calculate the coefficients. Right, so the theorem is the following. So suppose I'm given a function phi of x, which is defined between 0 and L. And I know that phi of x is written as an infinite sum from n equals 1 to infinity of an times sine of n pi over L times x. The conclusion is that an is given by 2 over L times the integral from 0 to L of phi of x times sine of n pi over Lx. dx. Right, and so the analogy with linear algebra, this is like, again, x is like a sum of ci, vi, and the coefficient ci is the dot product of x times vi, right? My function phi is like my vector x, and sine is like my vn, right? This is the analogy. And the integral is like the dot product. Right? The only difference is we have this 2 over L factor here. The reason the 2 over L is there is just because I wanted to integrate to 1 in the formula from the last theorem, so you need to scale by 2 over L. It's a minor thing. Okay, and so here's the proof, and the proof will be very similar to what we did in the case of vectors. What I'm going to do is, well, let's look at this integral. Let's get integral from 0 to L of phi of x times sine of n pi over Lx dx. In order for this argument to work, we would technically need some assumptions about phi. So we're going to assume that phi is sufficiently nice meaning it's not a crazy function. Understanding what actual like rigorous technical conditions you need is a more complicated problem, which we'll talk about throughout the next few weeks. But assuming the function phi is sufficiently nice, for example, if it has 2 derivatives or something like that, twice differentiable on the domain, right? So in fact, you can probably have weaker assumptions, but assuming this is the case, well, what we can do is I can plug in this formula for phi, right? So plug in this infinite sum. Well, I'll sum over m as my index because I don't want to confuse with the m with the n from the integral. Right, so I have this infinite sum all times sine of n pi over L dx. And so what I'm going to do now is I'm going to write this as the sum. I'm going to interchange the integral and the sum. And so this is where we need a certain hypothesis on phi in order for this to work. Let's not worry about it too much. So let's say that this is equal to integral from, or sum from m equals 1 to infinity, integral from 0 to L of am. Well, I can factor out the am because it doesn't depend on x. And then I'm just left with sine of m pi over L times x times sine of n pi over L times x dx. Okay, but by the previous theorem, this integral is equal to L over 2 if n is equal to m and 0 otherwise. Right? This is just the previous theorem. And so there's only one non-zero term here. And the only non-zero term is when m is equal to n. Right? So this is now equal to, well, there's only one term, which is an times L over 2. And that's it. Well, on the left-hand side, I have the integral of phi times sine of n pi over L times x. And on the right-hand side, I have an times L over 2. So if I just divide by L over 2, this tells me that an has to equal 2 over L integral from 0 to L of phi of x times sine of n pi over L x. And so that proves the theorem, right? That's what we wanted to show. Right, and so this quantity is called the nth Fourier, the mathematician who discovered this, sine coefficient. Right. The reason it's called the sine coefficient, again, is because it involves sine functions. Momentarily, we're going to talk about an analog of this for involving cosines. And then next week, we're going to introduce a version of this using just complex exponentials, which will combine the two interpretations. Maybe we'll say a little bit about this beforehand also. Okay. And so I do want to make a few remarks about this theorem. What this says is that if we know we can write our function in this manner, then the coefficients have to satisfy this formula, right? So I have to be able to calculate the coefficients in this manner, right? And so you can ask a converse question, which is like going in the reverse direction. And so the converse question is the following. Let's say we are, suppose we're given some function phi of x on the domain between 0, phi is defined between 0 and L. And suppose we define the Fourier sine coefficients as above. Right, so suppose we define an is equal to integral from 0 to L normalized phi of x times the eigenfunction, right? Sine of n pi over L x dx. Is it the case that I can write phi as this eigenfunction decomposition, right? Is phi going to be equal to this infinite sum, an times sine of n pi over L x, right? Okay, and you may object like, oh, didn't we just answer this question? Like that's what we just proved. Well, actually, no, that's not what we just proved. Because if we go back to this theorem, we're assuming here that we already know my function phi has this representation, right? So we're assuming I can write my function phi in this way. And the implication here is that if you can write phi in this way, then an has to satisfy this formula, right? So the question down here is, well, let's just suppose we're given a function phi. Of course, we can calculate these coefficients, right? It's just an integral. For a given function, presumably you would be able to calculate this as a number. And then you can define the series. And the question is, does this series represent your function or not, right? And so this is like the central question to something which is called Fourier analysis. Which is the topic for the next several weeks, as I've been repeatedly saying today. And so this is one of these questions that motivated like centuries of mathematics. And so a lot of the major contributions, and really in both physics and math in the 1800s and the early 1900s, and even continuing into the 1900s and beyond, were motivated by questions of this type. Right, so Fourier analysis is like a major topic in math, and you'll be exposed to a little bit of it in this class. So one thing to point out is that we need boundary conditions for this to hold, right? So if phi has this form, right, sum of n an times sine of n pi over lx, then phi of 0 has to equal 0, and phi of L has to equal 0, right? Because if I plug in x equals 0 or x equals L to these signs, I always get 0, right? So you need the boundary conditions. So this is like a necessary condition, but otherwise it's a harder question. Okay, and so for the last part of the lecture today, we're going to look at an analog instead of sine series, we'll be looking at series involving cosines. And so it turns out you can ask the analogous question where instead of sine of n pi over L, you have cosine of n pi over L times x. And this is also related to a particular boundary value problem in partial differential equations. And so we're gonna start reviewing this and maybe finish up the discussion on the next lecture. So the next thing I want to talk about, right? So the next thing will be cosine series and something called the Neumann boundary condition. Okay. And so what we're going to begin with is try to connect this back to studying PDEs. And so we're going to consider a different boundary problem. So in this case, let's look at say we look at the diffusion equation, ut minus k times uxx is equal to 0, defined for x is between 0 and L, and time is positive. Right? So we have a finite x domain, although we're letting t go to infinity, as we saw before, with the following boundary conditions. So we're not going to assume that the solution is 0 at the boundary, but we're going to assume that the first x derivative is 0 at the boundary. So this is equal to 0, and the x derivative at L for all time is equal to 0. Okay. And so this is something that's called the Neumann boundary condition, named after the mathematician Neumann. So for the previous problems, we were looking at something that would typically be called like the 0 boundary condition. This is a boundary condition involving first derivatives being 0. So this is typically called the Neumann boundary condition, or the Neumann 0 boundary condition. Right. So for these types of this models problems in partial differential equations or problems in physics, where maybe you're not interested so much in the initial position, you're not interested so much in the values of the solution, or in imposing conditions on the values of the solution itself at the boundary, but you want values of the derivative of the solution at the boundary. And so this could impose certain conditions, right, related to like the flux of whatever u is measuring as it leaves the domain or something like that, right? Because flux involves derivatives. Right, okay, and so you can solve this boundary value problem using the same techniques that we saw earlier. So using the separation of variables technique, as with earlier examples. And so this will be another problem on your homework 6. So you get more practice with separation of variables. And again, I'll give you some hints to guide you through the solution. And after using this technique, you arrive at the following guess for a solution. It's going to look very similar to the formula we saw with zero boundary conditions, but instead of having sines everywhere, there's going to be cosines everywhere. And so the following is a guess for the solution. U of xt. Well, I have an initial term which corresponds to n equals 0. So say 1/2 some number a naught or a 0. And then I have an infinite sum of so some other coefficients an. And then I have this exponential term, which we saw before when we looked at the same equation with 0 boundary conditions, kt. And then I have and now instead of a cosine, or sorry, instead of a sine term, I have cosine term. Okay. And so in particular, well, right, so you'll work through the separation by variables, separation of variables technique, and you'll arrive at this guess for a solution on your next homework. And so the main difference is, well, for one, we now have a coefficient corresponding to n equals 0, right? And so this is necessary because the cosine of 0 is not 0, right? And so in particular, my solution when x is 0 may not be 0, and so I need some other number here, right, potentially. I mean, in fact, you can think of this as a0 times the cosine of 0, right? Because, I mean, cosine of 0 is 1, right? Cosine of 0 pi over Lx, because cosine of 0 is 1, right? Well, now let's say we also impose initial conditions, right? So suppose u of x comma 0 is equal to phi of x. Well, what happens if I set t equals 0 above? Well, then I would need phi of x to be equal to, well, the only thing that depends on t is this exponential term. And when I plug in t equals 0 here, I get e to the 0, which is just 1. So I get 1/2 a0 plus now sum from n equals 1 to infinity of an times cosine of n pi over Lx. And so this is called a Fourier cosine series. Okay. And now we can ask all sorts of analogous questions about this series when compared to the sine series. And it's going to turn out that there are very similar formulas for calculating what the coefficients would have to be. And there's also a nice interpretation in terms of eigenfunctions for a certain operator. And so I'll begin the next lecture by going through all of this. So we'll return to this problem and I'll discuss cosine series. And then it's going to turn out that for more general functions, you're going to want to combine sine and cosine series together. And so this is going to lead to the notion of what's called a general Fourier series, which we'll then discuss for quite some time for the next several weeks. Right.